Wait, it says on here a premium account on Twitter is required for live broadcast now. They just made that change apparently. Wow.
Oh,
That is interesting. They just forced that. Oh man.
I
All
guess
right.
you
Let
gotta
me
upgrade now. You gotta
I'm gonna
upgrade.
I have to do it right now. Thanks, Elon. Hey
Elon's
Randall,
got you.
Randall,
He's
can you
got you,
post a
bud.
comment? Can you post a comment that says I'll be right back? I gotta upgrade Twitter now real quick. Just post a
Me?
comment. No, Randall, he's in the background
Oh,
listening.
okay.
All right, let me go and do this real quickly here. How do I do it? Elon Musk. Thanks, Elon Musk. Twitter premium. There we go. Basic premium. Okay, subscribe. And I didn't think he was ever going to get me. He got me. Right,
He got you.
1124. 825. All right, let's see if this works. All right, I just made payment. Let's see if it upgrades. All right, it says it was good. You're all set. Purchase successful. ID verification. I'll do that later. All right, let me see if this actually works. All right, let's try to go live again. I think I was live that whole time. I think it might have just let us go there. So can you guys hear me and see us right now? I see there's some hundreds of people already on, so I'm assuming you can. So,
so did Twitter just trick you into upgrading, but even though you didn't really need to?
No, it automatically, as soon as I paid, it just went live. So, okay, we're live. Okay, thanks, Jonathan. Great. Okay, on YouTube, obviously. Yeah, I know YouTube, but I don't know on Twitter. I'll go check Twitter right now real quick to say, oh, I just got a celebratory confetti that just showed up on my Twitter screen here. How amazing. I'm going to see if it's streaming. It does not show that it's streaming. So I don't know why that's the case. Okay. I'm just going to go forward because we don't have time to waste on that. Let's start. That was an interesting introduction here, right? So welcome to the Off by One security stream on this Friday, July 26th. So as you probably saw, I just went to go live and it said you can't stream to X now because you have to pay and be premium member. I thought I was going to be able to get away with not doing that, but Elon finally got me, so I just had to make payment. And then when I did that, I think it just automatically started the stream without letting us know, without me having a chance to do anything in the middle. Jonathan says not streaming on Twitter. Oh well. Wait, it's got an exclamation point. Go live. All right. Let me see if it's working now. A premium account is required. I'm premium now, man.
Are you premium or just half premium? Because Twitter now has 2 levels of premiumness, you know. I'm not kidding. There's 2 levels. There's like semi-premium and really premium. And you have to be the ultra premium, which is the more expensive one.
It says I have to unlock to upgrade articles. I don't know. I don't have time to deal with this right now. The upgrade, unlock all features.
Yeah, you're not really premium. You're probably the half premium.
All right, I'm going to upgrade and just hope that it magically works. And if it doesn't, oh well, I'll deal with that next time. So while I'm doing this, for those of you watching right now, welcome to the Off by One security stream. It says something went wrong. I'll deal with that later. Let's just get going. So I have Casey Muratori on. And like I said, as we were going there, Twitter said, nope, you can't stream to us. So, oh, well, we were not streaming to Twitter. This has been a session that has been requested by a lot of people. Specifically, people were saying, can you get Casey on? And thankfully, he was like, I don't hack for a living all the time, but I'm willing to entertain your questions. So thankfully he's come on, which I know a lot of people have been looking forward to it. And the thing we're looking at here is low level stuff, microarchitecture stuff. A lot of us, we know that there is an instruction pointer or a program counter, and it points to a virtual memory address. And that's the next address where code execution will continue. And then magically, something happens and it executes. But we don't know. We care about getting control of the instruction pointer to redirect the flow of execution, but we don't necessarily know what's happening inside the processor. And we've heard about many, many hardware attacks over the years, Rowhammer and just tons of them. And a lot of people who have done exploit development, vulnerability research have pretty much stayed at the application side, into the kernel too, maybe, but not so much on the hardware side. So I think that Casey is going to really help us get a good view into that, what it looks like, kind of how to go in that direction. So Casey, if you want to give a little bit of background about yourself, I think that will be helpful. And thanks again for joining us.
Oh, it's my pleasure. Thanks for inviting me. As I said when you invited me, I hope I can provide some useful information. Obviously, I come from a very different background. I don't try to exploit hardware at all, never have. I come from actually a game programming background. And one of the things that we care about in game programming, of course, is performance, right? What we're mostly concerned about is, at least on the game engine side of things, what we care about is trying to get the most out of your processor, right, and your GPU. And so the way that we have looked at things traditionally has been, how do we analyze what the hardware is doing from the standpoint of getting it to do more? That's where we're really coming from. And so, interestingly, this kind of overlaps security research occasionally, because when security research gets down to the strange hardware tricks kind of stuff, it is in the same kind of microarchitecture realm where it has to understand exactly how the processor works, as we are in software performance, where we're also trying to understand those things, but just from a very different perspective. We don't really want to exploit anything, but we do want to try and, make things run faster. And so what I usually focus on is that side of things. Like, how do we get more performance? How do we look and understand what the hardware is actually doing, so that we can figure out how to write more efficient software? But it sounds like, I guess, from the fact that your audience has apparently at least must know some of the stuff that I do and requested that I come on the program, it sounds like you folks also want to look at that kind of lower level stuff. And so hopefully I can provide some useful information there, maybe pointing people towards the kinds of resources that we use when we're analyzing performance, so that you can translate them into a security context and do what you guys need to do with them.
Yeah, sounds great. And I think for a lot of people too, it's like when the attack surface starts to get so challenging, so difficult, where all these mitigations are there, which I talk about and complain about them often. People want to go look at different attack surfaces, and not to say there's it's free of security mitigations, because there's plenty of them that have started to show up. I remember when Project Zero started really taking a look at Google at the hardware attack surface and started to find a lot of great things. And of course, what follows is mitigations and more security.
Yes.
Yeah. So great. And you have a channel, right?
Well, yes. Actually, I post. I have a Substack. It's called computerenhance.com, and that's where I post all of my educational materials now. So that's where they're there.
Awesome.
Yep.
Great. We'll get all that stuff posted in the comments as well. Just before I forget, a quick thank you to members who have signed up and are members. That's really awesome that you've done that. And it's been a huge help in, as you've probably seen in prior streams, getting us to be able to give away things back to the community, even more than just information. We were able to get a couple people over to DEF CON that's coming up there and get a hotel covered and flight and entry. And it's really, really cool to be able to do that stuff and get it to people who otherwise wouldn't be able to attend. And it's things like membership and donations and all that really help make that possible. And also meeting with the Miscreants folks while I'm at DEF CON to hopefully get some merch created. I got to hook my mods up on Discord and also get it out. And I want to make it so all the proceeds from that as well go to charitable type things. So just again, a big thank you. If you're going to DEF CON, I'll be there. I'm speaking on Saturday at 11 a.m. In one of the main track rooms. I don't know which one it is exactly. Holds 1,500 people is what I'm told. And it's going to be hallway con again, but hopefully that's enough space for folks who want to come in and say hi and see the presentation. It'll be on the rise and fall of binary exploitation. All right. Again, as usual, if you have questions, please do post them in the comment section. I will try and moderate them if they're tied to what Casey's talking about. I also don't want to interrupt him if he is on a, on a tear talking about something, and you don't want to try to derail people. So, but please feel free to ask him. And if we don't get to him while he's talking, we'll get to him and leave a little bit of time at the end. So Great. I guess why don't we I mean, you tell me if it doesn't make sense to start here, but why don't maybe we should start at the thing I brought up first, which is when you see a virtual memory address and the instruction point is pointing to it, we were always told that's the next address where code execution will continue. Like when we do a call instruction, the call instruction takes the next virtual memory address, pushes it onto the stack, right? And then we return to that later. So what actually happens when we hit an address and we go to do something?
Okay, so let me try to rewind a little bit from there because so the way you just described it was sort of the way that it might have worked in 1995, right? Uh so it's an accurate picture from the programmer's perspective, meaning
Yep.
that is what we are. The best way to think of it might be we have this thing called an ISA, right? An instruction set architecture. And we give them names, like a particular ARM ISA, they've got names. There's the x64 ISA, which is probably what you do a lot of your security research on because it's, very popular in the server world and on desktop PCs and so on. And that ISA, you can kind of think of it as like a promise to the programmer. And that promise includes specifications for what's going to happen in everything you do. And the promise of what's going to happen is sort of what you just described. It's like, okay, there's this thing called RIP that is this quote unquote register, and it's going to hold this instruction address, and we're going to go fetch that. And, a call is going to push something onto a stack. The stack is an RIP, whatever, right? There's all these things that it says that are going to happen. And that used to be a fairly direct, like, to some extent, that was a fairly direct translation from that promise to what was happening on the chip. Now, even back on the original 8086, it's less of a direct promise than you think. When you go back and look at how something like an 8086 worked, you'd be surprised at how not quite as direct as that it really was. But if you fast forward to today, that promise is literally just almost like a spec that the hardware designers know it has to look like the chip is doing, because that is what the software needs in order to be correct. But it happens nothing like that. Like what happens inside the chip is completely different than what that would sort of portend. So if you don't mind me taking a little bit control of the screen here, maybe I can bring up a few things, a few diagrams to kind of show you what I mean by this. I can kind of switch over to my computer here. And I tried to bring up a bunch of things that I thought might be useful depending on what questions you asked. And this one actually would be pretty relevant.
Yeah,
So
you're right.
this, oh, sorry.
So I
What?
was going to say before you get started there, you reminded me of a bad memory from an interview at VMware that I had, where the guy asked me to explain how optimization of translation look-aside buffers would work in the kernel on hypervisors, and the question was longer than that. And I started to go into like memory translation from virtual to physical and how you index into the page tables and the PTEs and the control register 3, all that. He goes, you don't look that old. And I was like, what? He goes, and
Yeah.
he's like, you just explained to me 32-bit, blah, blah, blah. And it was just hysterical. I'm like, man, okay. Works in my head anyway.
Well,
All
I
right.
mean, it's one of the problems is this stuff moves quickly, right? It's every 10 years, it's like completely different. So what can you do? But anyway, this right here is an example of what you would see if you like this comes from a presentation by AMD. That's like what they put on the screen when they're talking about the Zen 4 architecture. This is what was the Zen 4 diagram that they showed in their slide presentation when they were like announcing it, right? And if you look at a diagram like this, what you can see is that there is a really bizarre contraption that they have designed in order to execute instructions. And I want to call out a few points. Can you see my little cursor moving here?
Yep.
So what actually happens when the CPU is executing your instruction stream is, first of all, when they started moving to CPUs that had to get speed from things other than the clock rate, Like in history, if you look, there was like a whole period when consumer CPUs just got faster by increasing the clock rate was like the main thing, right? It's like, oh, it was 500 megahertz. Now it's 800 megahertz. Now it's a gigahertz. Now it's 2 gigahertz or whatever, right? At some point, around the Pentium P6 era, they kind of hit this wall where they couldn't just straight increase clock rate as well anymore. There was like heat barriers and other kinds of problems, and they kind of hit this wall. And I'm not a hardware designer, so I'm not, capable of explaining exactly details of why that was. But as a result, what they had to do is they had to start figuring out a way to make consumer chips do more work in one clock cycle than they used to do, because they weren't going to get much anymore from just cranking that clock speed up. So they had to do something else. And so that kind of began this era where it was all about IPC. You've probably seen this, instructions per clock, right? And if you think about what that means, instructions per clock, well, baked into that is like, we're trying to do more than one. On a clock cycle, we're trying to execute more than one instruction. Otherwise, we wouldn't be talking about IPC. We wouldn't say we're trying to get an IPC of 3 or 4. We'd be saying we're trying to get an IPC of 0.5 or something, right? So instructions per clock, more than one. And so what you can think about when you think about microarchitecture is the machinery of a chip, of a core, that's designed to figure out how to take more than one of the instructions that you are feeding it and execute them on a clock cycle. So that's going on. And then, because you're trying to do that, there's sort of this issue that happens with the kind of code that we... first, I should pause. Is this too much detail? Let me know if I'm off base here.
No, this is great.
Okay. So the other thing that happens along with IPC, if you think about it just kind of logically, if the CPU has to issue more than one instruction per clock, if that's to figure out how to get more than one instruction done per clock cycle, you end up in this nasty situation where most code, if you look at the instructions that are like very close together in the instruction stream, they tend to like depend on each other. It's kind of like test this thing and then jump if this thing is true, or add this number to this number and then multiply it by this other number. And the problem that you get when you look at those kind of instructions is, unless the compiler or the assembly language programmer has done a really good job interleaving instructions in some way that makes them easy to makes them not be dependent on each other in a local area, the CPU couldn't really execute more than one instruction at a time, because all it's going to see in that little window are dependent instructions that it would have to wait to execute until it finishes some other instruction, right? And so out of that grew this idea of out-of-order execution, which is how all modern high-performance CPUs work. The idea is that they are going to look at a very wide window, hundreds potentially of instructions that you are feeding it. They're going to consider all of that and try to look for independent bits of instructions, right? Independent instruction, like, if you think of these little serial dependency chains, I do this instruction, then this one, then this one, they all depend on each other. But in some other place, there's a few other instructions that depend on each other, but they're two separate independent streams that don't depend on each other. The processor is like hunting for these. It's trying to pull out things that are independent so it can execute them at the same time. And so when we see a modern microarchitecture diagram, what we are looking at effectively is a machine for pulling out independent work that can happen at the same time and trying to do as much of that independent work as possible. Does that make good sense just philosophically?
Yep, perfect.
Okay. So this is the example of a microarchitecture diagram that an IHV will publish and share with you. And it's separated conceptually into two pieces that they typically talk about separate. I mean, technically it's three pieces here because you have like a memory hierarchy here down at the bottom. But the two pieces we typically talk about are called front end and back end. Front end is this part up here in blue. Back end is this part that's a little more colorful in orange and red. And the job of the front end is to build up that window of possible things the processor could do. A giant sort of queue of possible things that it could work on. And so you can think about the front end of the processor as taking the instruction stream that you're used to thinking of as happening step by step. right? Like you gave that example of RIP and a call instruction. It's like, oh, there's a call instruction. So we will push some registers and we will push the RIP and we will do these things as a series of operations, right? We're thinking about those things in order. And the front end's job is to take that ordered instruction stream and just turn it into a crap ton of work that the CPU could do that it can analyze for independence. And the way that it does that is you see up here in the corner, there's this branch prediction box, right? The branch predictor on a modern CPU is massive. It's this huge thing that, again, maybe a little bit too much detail, but for security research, you really care about this part. So I'm just going to harp on it. In fact, let me see if I can bring something up here. This may be really in the weeds, but sorry, we're off on a tangent now. But hey,
is it tied to speculative execution at all?
Oh yeah.
Okay.
So if we pull up something like a Zen 4 die shot here, I don't know if we can get one. Let me see if I can just look at what this looks like, so people can get a sense of it. Yeah, here we go. So if you look at something like a die shot, like the actual physical silicon of the flowchart I was talking here, this here is like what is probably the branch predictor, right? It's huge. It's like, here's the L2 cache, here's the branch predictor. See what I'm saying? So there's a massive amount of space on the CPU that's dedicated to the branch predictor. Why is this? Well, if you think about what's going to happen in your code, you're feeding it an instruction stream, and I just said it's got to look at a very large window. So what it needs to do is it needs to, the front end part that's handling these instructions and figuring out what they do, it has to look way further ahead than you have actually determined where the code will go. You've got a bunch of things that are like if statements and while loops and whatever that in assembly language translate into comparisons and jumps on flags and things like that, which I'm sure everyone in the audience here is probably familiar with, because when you look at disassemblies, that's what you're looking at, all of these different types of jumps, right? Call would be another example of a jump. It's just a jump that does a little more work, right? And so what the front end has to do is it has to run through all of these instructions and just guess. It has to guess where the instruction pointer is going to go. And so this brings me to the first point that I wanted to make based on the thing you said, where you're like, oh, there's this RIP, there's this instruction pointer and it's got a virtual address in it, and that's where we're going to go next. So the first thing to internalize is no. The front end was way ahead of you before you ever asked that question. The front end, by the time that you ever actually know what the value of the instruction pointer is going to be at some point in your code, the front end could have been 100 instructions in front of you, having guessed at what the value of that instruction pointer would have been the entire time. At every jump and call and other kind of instruction pointer change in your code, this branch prediction logic was guessing where you would go. And that's what it was actually decoding for your instruction stream. Does that make good sense?
Yeah, perfectly. It's great.
Okay. So the way this machine is operating is it's running through code. It has an iCache, right, which is basically just, we talk about the level 1 cache. You got L1 cache, L2 cache, L3 cache typically, maybe even L4 cache depending on the chip, and then main memory, right? It's got a memory hierarchy. I won't go that detail. I assume most of your audience knows what those things are.
Yep.
But the L1 cache, right, again, because, and, go back here to the chip diagram if it's ever confusing. When you get to the L1 cache, these are things that are designed to be the fastest possible access for the CPU. And they need to have incredibly tight timings to get data to things like the register file and the instruction decoders and whatever, right? And so by the time, the L2 cache is like, here it is on a Zen 4 core. The L2 cache is this big thing that holds both instruction and data pages. Whenever you're fetching instructions or you're fetching data, it's asking the same cache to get both of those things at the L2 level. But at the L1 level, because those things have to be very, very fast, they're typically split on the chip. And you can see that here. Instructions are cached in this cache. Data is cached in this cache. So that's why whenever you see, if you've ever looked at processors, they're like, how much I cache, which is instruction cache, and how much data cache does it have at the L1 level? You almost never see it broken out that way on L2, L3, because they're not, right? But at L1, they are broken out that way. And again,
I'm used to seeing this per core, and an L3 is a shared cache between the cores.
Exactly. It depends. So there's L2 is sometimes also shared. Like, for example, an Apple M series processor is more of a shared L2 cache. Whereas on something like a Zen 4, it's a private L2 cache. So it really just depends on the processor architecture, how they structure it. L1 is like never shared because it has to be like welded right to the things that need it, right? Like, because it's got to be so fast. And so coming back to the diagram, the way this is working is the branch predictor is guessing what the next instruction pointer is going to be, right? Anytime it's not just going to go in order, the branch predictor is guessing where it's going to be. The instructions obviously come from memory. So it fetches a cache line, right? Or potentially more than one, depending on how fancy this chip is. It fetches the cache lines that it thinks the instructions it's going to have to decode next. It fetches wherever they're from and brings them into the iCache, which is this little smaller cache that just holds instruction cache lines from memory that hold your code. That feeds decoders, and sometimes there's only one decoder. Nowadays, there's usually more than one decoder, and they try to decode multiple instructions in parallel. This is very easy on something like ARM, where you kind of know where the instruction boundaries is. It's a fancier process on x64, where it kind of has to do more guesswork about where the instruction boundaries might be, since instructions can be variable length. But point being, they're trying to decode multiple of these. And the decode turns your instructions into micro-ops. Now, most people are probably familiar with what micro-ops are, but just in case they aren't, just really quick. Some instructions, especially on x64, as you probably know if you're a security researcher, you read assembly language code all the time, some instructions are really complicated. It's like this one move instruction, but it's got a bunch of arithmetic based into it that, says take this register and add it to 4 times this other register, and then fetch that and move it into this other, right? Instructions can be more complicated than just a very simple thing like add or, right? And so what the decode process does is it takes that instruction stream and it turns it into the simplest possible operations that the core actually knows how to execute. And sometimes that's going to result in multiple of these micro-ops for one instruction. So at this front-end boundary, after we hit the decoder, we're no longer talking about instructions like the kind that you see when you look at a assembly language, routine. We're talking about some internal, not documented, secret kind of instruction. And we call those micro-ops. We don't exactly know what they are, right? Intel doesn't print a list of here are the micro-ops exactly, right? But that is what the processor will then actually execute. A processor never really executes your instruction. It executes micro-ops that result from your instruction. And those decoded micro-ops, they all go into a queue that feeds the second part of the chip, which is what we call the back end. And they're not rigidly delineated. Those are just sort of theory terms that we use to talk about the two different parts of the process. Okay, so that's the front end. Does that make sense? It's a thing that chews through your instruction stream as fast as it can using guesses, right? And various caching. There's a micro-op cache sometimes. Modern chips are sort of ditching this. Like Zen 5 doesn't even have one. But sometimes they cache things they decode, the micro-ops they decode as well. But that's sort of falling away a little bit. But point being, they at least use an iCache. And then they produce this queue of instructions where they've just blasted really far ahead to try and figure out all the things you might be doing in like the next 100, 200 instructions, right? It's going ahead. Does that all make good sense?
Yep, it's great.
Okay.
Jonathan Ryder asked, for gaming, is it important to design your structs to be aligned to cache line boundaries?
Yes and no. It really depends on what you're doing. That's kind of a totally separate topic because that's the data side of things. And the answer there is usually cache line boundaries have to do with your access pattern and whether or not you're talking about multi-threading. So I would say maybe hold that question if we can get to it later. But that's like a whole other topic of like why and when you need to align things to cache line boundaries, because it really depends on what you're doing with them. Sometimes you don't want to align to cache line boundaries because you're trying to pack as much into a small space as possible, so padding would be a bad idea. Other times, if you're talking about things like avoiding false sharing or trying to make sure that you don't fetch more than you need to fetch, then cache line alignment can be very important. So it really depends on what you're doing. That makes sense.
Okay, great. And one other quick one. This might not be a good time for it, but what mitigations are in place for branch prediction penalties?
So I'll be completely frank. That is really more of a security question. So mitigation-wise, I could not tell you. In general, my expectation would be that if the processor is not executing in like, so there's, I assume you guys are familiar with DIT and DOIT, the two like sort of Intel and ARM both have different specifications for this sort of data independent timing stuff that they do. Does that ring a bell for anybody?
Yeah, I mean, I've heard of it. I'm not sure about everybody, but yeah.
Okay, so there are things that processors introduce that are sort of special modes. But if you're not in one of those modes, there isn't really a mitigation for branch prediction penalties that I know about, at least not on the performance side that I've ever seen. But that may be just because I don't do security research. Maybe there are some mitigations that have happened there. But again, for performance, we don't really look at things in terms of mitigations. If something gets slower, we see it on our benchmarks and we try to shuffle. But it's not something that I would be like, oh, yeah, they mitigated this from here to here or this firmware update. It's not something that I track. But generally, I guess let's skip a little bit of the back end here and let me talk about that, and then we can come back to the back end. So generally, let me just say what a branch prediction penalty is. So that all happens based on guesses. And the branch predictor is making those guesses very educatedly, right? It's tracking statistics for all of the jumps in your code. And it's figuring out like, oh, I think they're probably going to go here because it looks like this particular comparison, this jump happens with this kind of frequency. It isn't taken 4 times and then it's taken once, and then it isn't taken 4 times and it's taken once. So I think this is a predictable loop, and that's what I'm going to guess, right? So there's pretty sophisticated stuff that it does with respect to that, and but it's never perfect. So what happens is if the front end guesses wrong and it decodes ahead quite a bit, then you'll pay what the questioner sort of said, a branch misprediction penalty. And what's happening there is you have to think about this whole thing as a pipeline, right? I've got this giant queue that I filled up. I've got this back end, which is trying to execute things out of that queue. And it's got multiple instructions potentially in flight at once, which we'll talk about in a second. If you guessed wrong, then the processor has to do several cycles, usually somewhat proportional to the pipeline length of the processor, which is like how many stages it goes through and executes things. 10, 14 cycles, things like that. It's got to sort of flush a bunch of work that it was doing, and that queue has to like refill. The front end has to like start over. It gets basically it's almost like a panic from the back end, right? It's like, that prediction you made is wrong. All this stuff in the queue is wrong. Restart from here. This is the actual value of the instruction pointer that you should have guessed and didn't. Restart. And that sort of flush and restart costs you a bunch of cycles. And again, in performance, where I come from, all we care about is not letting that happen, right? We're trying as hard as we can to make sure that our branches are very predictable so the processor does know what they're going to be. I would imagine, and again, I can't speak to it because I don't do security research, but I would imagine on your side of the fence, you're trying to figure out how to make it do interesting things with branch misprediction, right? Getting the mispredicts to change timings in ways that you can observe that tell you something about what the values were involved in that branch, which will like leak some critical information, right? And so in terms of mitigating that, I mean, there really aren't any mitigations that I know about that happen in normal execution, but I suspect there would be when you turn on some of those data independent modes. I don't know, like those probably do stuff And again, we never turn them on in performance because we would never want that. But that could be a thing. So moving on to the back end here. So all of the, you've got all these micro ops building up in this queue. And then you go into the execution, the actual sort of doing the work, right, part. We've done all the decode to know what we're supposed to do. Then we need to do the work. And what happens is the processors now have sort of lots of execution units. These are things that can do various operations like adds and ors and shifts and address generation, multiplication, all that stuff. And if you look at one of these diagrams, they're represented down here in these boxes. So you can see there's two sides to this. They're labeled integer and floating point a lot of times, but that's not what they are. What they actually mean are this is the general purpose register side. So think when you're looking at assembly, RAX, RBX, RIP, those sorts of things are all kind of considered to be on the general purpose side of things. This side labeled floating point is actually the SIMD side. So this is all the stuff that's like your SSE registers, your AVX registers, right? Think XMM0, YMM12, that sort of stuff, right? And so what happens is all of the micro ops that the processor can look at, it's trying to figure out effectively which of those it can do at any given time. And the various execution units here, it's trying to feed as many micro ops as it can on any given cycle into as many available execution units as it can find. And on each cycle, it starts putting things in execution units until it can't find any more to put, or it's run out of capacity for that cycle. Because typically, like you see, there's way more execution units here than a processor can typically do on one cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? There's way more than 4 or 5. And that's what these kind of era processors could usually do, 4, 5, 6. Newer era processor can do 8, but there's always way more execution units than that. So they're sort of there's more execution units than it could do on a given cycle. And that's because they do different things. So they're trying to kind of have a balance of hoping that the kinds of micro ops that they see on a given cycle, that they will have some execution units that can accept those and enough of them that they can do a bunch on that cycle. Now, let me say one more thing before maybe I give it back to you and you can ask a second question. So I guess two more things. So you'll notice here at the top, there's a thing called integer rename and floating point rename. So this gets at sort of another thing that was implicit in your question. And that is that there are these things called registers. So we talk about something like RIP, right? Or we talk about a more explicit value like a data register like RDX or whatever. We think about those things as being these data slots in the processor. And when we're doing disassembly or when you folks are reverse engineering something, you're looking and you're like, oh, what is the state of the registers at this time? Let me look at them. Here they are. Oh, RAX is this, right? But none of that is actually true either. What's actually happening is in these stages here where you have integer rename and floating point rename, what's actually happening is those names that you give things are really just so that you can tell the processor which data values you were talking about. But because it has to execute all of these instructions sort of in out of order, like grabbing some from later and grabbing some from earlier and whatever, it can't just have one place that it stores the value of RAX. Because the value of RAX may be one thing at this point in the instruction stream and something else at another point, and it has to track that. So what it actually uses is this huge thing called a register file, which stores many, 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 many values, like hundreds of values for the different registers that you're talking about. So at any given time, you think in your head, there's one value for RAX. And that's the value that it would be if the instruction stream stopped right here at this point that I'm looking at. But the processor doesn't think about it that way. It has a whole time series of registers where it's like RAX is this over here, and it's this point, and it's this other thing. And so it's constantly renaming effectively these registers to different data slots in this thing called the register file. And so that's what this part is doing. And so it's also important to remember, much like the front end is reading way beyond what you think of as the instruction pointer, The back end is also tracking way more registers than you are thinking of. You're thinking of 16, 32, 64 registers, depending on whether you're talking about just general purpose or all the AVX 512 registers and other things like that or whatever. Well, 64 might be a bit much, but you get the idea. And you're thinking of it that way, but it's actually way more than that because it's tracking them at different times. So finally, what happens is at the end of all of this, there's this thing called a retirement window or reorder buffer. There's different ways that they talk about it. And honestly, I'm not an expert at this part of the chip, so take it with a grain of salt. But because it has to appear to you, the programmer, as if these things actually just happened in order, there is a final stage where it has to sort of serialize things. And this is where it's sort of holding operations that might have side effects that are observable. This is where it's holding those until it knows for sure that something like a branch that it predicted in the front end will not go the other way. And so there is a stage where things then get linearized or appear to be linearized as they are retired. It's called retiring instructions. And that is where this sort of that branch misprediction penalty, right? That's where it's realized. It's like, oh crap, we just finally got the result of this compare, and the flag was this, and the branch was supposed to go this way. That's what we thought it was going to do. We just got the result of the flag back. It's the other way around. That's where that's when it finally detects it. And so when you see a lot of these original microarchitecture attacks, things like Spectre and Meltdown, those were kind of about realizing, well, Spectre and Meltdown, not both of them, because one of them's more about cache eviction. But I think, was it Spectre is the one that's specific to the speculative execution part where it didn't clear one of the values, that sort of stuff. Either way, that's when they started realizing, we can exploit this because the processor's actually doing some work, and that work doesn't get completely undone when it does that serialization step, and we can take advantage of observable side effects that come out of incomplete reversal of what's going on, if that makes sense. So I think that's hopefully that kind of, does that answer your question, or does that expound ridiculously enough on your I have an instruction pointer and saying, well, you don't really anymore. That all that giant spiel I just said is what's actually happening.
Yeah, for sure. It's great. It's got me questioning a lot of the things now that I'm looking at in debuggers, though.
Sorry, I mean, it's still No, you're seeing what it to you is the state, right? So.
Yeah, and it makes sense too. Like you take something as simple as you're checking the argument vector, and there's an instruction that says, jump if less than or equal, and it's obviously if you're well before that checking of the argument vector to do something based on that, it's easy for the processor to jump ahead, check to see where the argument vector value is stored, and then make that prediction based on that. And like that makes total sense. I'm just thinking more of like, when you're looking at the context structures in a process, and the context is typically where the processor control block and where that data is stored to store the registered values for the last time we were under the context of that process,
In the operating system, you mean?
Yep.
So one thing I would say just slightly there, I may have misunderstood what you said, but just in case. So the branch predictor in general, and I guess, when I say this, we don't always get complete details. So, this could also be wrong. But in general, the branch predictor, you wouldn't expect it to look at the actual values of things. Usually it's guessing. And what I mean by guessing is it's literally just tracking what you have previously done when you hit that point, when you hit that branch, and it's guessing based on that. So rarely would you expect the CPU to go look at a data value that thing may be. Now that doesn't mean it doesn't happen. It just means most of the time I wouldn't start my thinking there. If I knew for a fact that the CPU did that, sure. But in general, I wouldn't expect that. So just wanted to add that clarification. It's really more of just a guess based on previous patterns. And this is also why, like, for example, I believe in the original Spectre Meltdown papers that were published, for example, they talk about mistraining a branch predictor. So what they'll do is they'll feed kind of known branches to it by constructing the inputs to some attack E just so they know that a particular branch will always go one way with those, values, so that they can know what the branch predictor will guess when it hits the branch, even if they then feed it some slightly different data where they throw it kind of a curveball, right? So, so it really is more of like, you can almost think of it as like a perceptron model or a little like machine learning model now, where it's just watching what you do and trying to build like a little, Markov chain or whatever kind of thing in there. It's like, here's my guess. This is what I guess he's going to do. And so it's very susceptible in a security context, I think. Again, I don't write exploits for a living, so I'm not sure, but it's pretty susceptible to you manipulating its view of the world for a little while. So it starts to guess one way, and that is just what it will guess from now on, usually.
Yeah. Do you see any machine learning being used in the future at that low level?
It already is kind of, at least in terms of how they like to describe it. This chip right here, the Zen 4, describes their branch predictor as sort of a perceptron model. So what they're really doing in there, I don't know, but they're trying to do things more like, a sort of neural net like kind of thing. It's obviously it's not going to be like Chat GPT, right? But it's, it's doing it has to be done very quickly. So it's doing that kind of prediction within the limits of a very small, very quick circuit, right?
Yeah, and Daniel asked a good question here. What about interrupts and asynchronous type stuff, like with the branch prediction?
So interrupts, are not really going to do anything beyond what you would expect. As far as I know, and again, like I said, the giant caveat at the beginning of all this is like, don't do any security research. I have literally never tried to time things around an interrupt, right? Because in performance, we're never issuing interrupts in like rendering code or something, right? But in general, when the general model for when you have something where the processor is supposed to halt or wait for something else or do other things like that, it's really not going to do anything different than what it normally does. It's going to the extent that it can, make a guess. And if that guess turns out to be wrong, or if it's something that is not guessable, right, then it's just going to have to synchronize. And it will suffer that same kind of pipeline flushing sort of thing that goes on when you have a branch mispredict, right? It's going to do the same kind of stuff where it's like, if it can, an interrupt is a fancy word for I'm transferring control to some other thing from a table, right? So it's not going to like go out of its way probably to flush everything, but it's going to do whatever it has to do to transfer control and do, if there's something unpredictable about that process, I can't think of what it would be, but if there's something unpredictable and it doesn't guess right, then it will stall. Now, interrupts are a thing where, again, I'm really hesitant to say anything because I don't work with them, but that's also a place where some of the mitigations that you're talking about might have been put in, right? I could see them having to mitigate certain kinds of interrupt things that were happening for whatever reason. Again, don't know. Like syscall would be the same thing, right? Where you get these kind of things that maybe they have to do certain kinds of mitigations around that. And I don't ever claim to know any of that stuff, and I never look at it. But in general, you can expect the processor to behave normally, and anytime it has to, it suffers that kind of branch misprediction penalty kind of effect.
Yeah, it's great. No, it's great information. I'll post this up here. I'm not sure if it's a bigger question than what can be answered right now with the other things we want to cover, but what are the key differences in IPC optimization strategies between CPUs and GPUs?
Okay.
I said it's a big question.
That's not really a security question, but so I'll answer that one very brief, since I don't think it's really on topic for your audience. But
yeah,
very, 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 very different. The reason for that is if you want just a brief sort of like generally leaves out important details, but is generally true picture of the difference between CPUs and GPUs in your head. A CPU is something that is fed utter garbage code and has to try and run it as fast as possible. So it's going for looking at a serial instruction stream, like a thing that it got handed that says it goes in this order, because that's what you're giving it, right? And it's trying to look through a giant stack of in-order things and figure out what it can do out of order. As a result, things on the chip that are large, the branch predictor, out-of-order schedulers, right? Actual register renaming is happening, things like that. Decoders for complicated instruction, who knows, right? If instead you look at something like a GPU, it expects to be handed like pristine code. It expects to be handed code that's already been compiled in such a way that it is massively, massively inherently parallel. Like, it is expected to be handed an instruction stream where you're going to do the exact same operations on like a million things. So the way it actually gets performance is not by trying to execute multiple serial instructions per clock that it disentangled. It's expecting you to have already told it, hey, I'm going to do this like multiply on like all these pixels at the same time. So spread that news out to a ton of execution units and they're all going to do it, right? So if you look at a GPU, they don't have like a branch predictor. They don't go ahead. They are pretty much like in order or slightly simultaneous paired execution. Think Pentium, original Pentium kind of things. This instruction and a few subsequent instructions, if they happen to pair properly for the execution units, that's what it's doing. And it's distributing those across the chip. We can look at no, I said I was going to be brief on that. So brief, but that's generally what's going on.
Yeah, no, that's great. That's helpful. One last one for now, and then we'll move on. This one should be a pretty easy one, I think, is Daniel's asking, as far as I know, compilers used to try to introduce instructions with branch hint opcodes to help out the branch predictor. Casey, do you know why that's not a thing anymore?
I mean, again, I'm not a hardware designer, so I always feel unqualified to answer the why it's not a thing anymore answers, because as much as I would love to know, I don't have the hardware background. So if I had to speculate, I would say it's because branch prediction is just so damn good now, right? I mean, a massive part that hardware designers were just like, look, we can keep getting these branch misprediction penalties down to less and less and less percentage of branches. And that was just very good for their benchmark performance. So they just kept making the branch predictors more and more sophisticated. And so I think probably what happened was just, if I had to guess, it's just like, look, we don't need the hints anymore. We don't need them anymore. Like, the prediction's just better than that. That would be my guess, but take it with a massive grain of salt. I'm not a hardware designer. I don't know why they do what they do. I have no idea.
No, that's a good guess. You're probably spot on, I'm sure. Cool. All right. Well, let's maybe switch over to the other planned topic that we were going to cover around performance.
Okay.
All right. So I'm trying to... Twitter is not behaving the way it was before I did the upgrade thing, and now it's acting very strange. So,
okay.
So let's take a look at performance metrics to the use of timestamp counters and how we already looked at how code execution takes place to an extent. So, trying to see if I can get you a better kind of starting question there, unless you want to just jump right in.
So from a security research standpoint, is the question basically like, I'm just trying to guess here. Is it basically like what sorts of things do I want to kind of know to get me started on analyzing a microarchitecture's behavior so that I can craft new exploits? Is that generally like what the idea is behind understanding things like instructions and timestamp counters and things like that, and how the CPU processes things? Or is...
Yeah, I mean, absolutely. It's like,
okay,
understanding what you know with the security spin on it, like what.
Okay.
Basically spot on. Like, I mean, everybody wants to know everything, but obviously we can't know.
Okay.
All of it, so.
Okay. Okay, so let me flip over here to some reference manuals and just try to give you an idea of like the kinds of things that you probably want to look at and familiarize yourself with so that you can start kind of down that path. If what you're primarily concerned about is trying to like time and exploit, I'm going to call it statistical behaviors. I mean, the way that I would say it is when I look, the limited amount that I've read security research, like for example, reading about like Spectre and Meltdown or, S-Box attacks on the original like AES stuff. Things like looking at the M-series data memory dependent prefetcher exploit, for example. A lot of these kind of new side channel attacks are about statistical things. They're like, we're going to time something, and an individual read of a timer isn't really going to tell us anything because it's noisy. But if we look at things enough, we can kind of look that there's like a shift. It's like most of our timings come back a little bit higher this way than the other way. And that gives us the leak, the leakage we need to determine what the bit was, right? That we were trying to attack or things like that. And so I think there's I want to draw a distinction between two things here. And I'm just drawing that distinction based on my sort of vague intuition about the sorts of things you folks do, because I don't really know. So I would say if I was going to go be a microarchitecture hacker, I'm thinking two ways. One is, what does the actual exploit look like? And that typically has to be using a very limited set of things. So limited, in fact, that on something like the M-series exploit that I just mentioned, the DMP exploit, that can't even use a high-resolution timer because that's been nerfed in the hardware at user level. So programmers who are programming to try and exploit Mac chips, they can't even call the high-resolution timer to look at it. So they had to do a thing where they just have a separate thread that runs, incrementing a variable as fast as it can, right? And so some other thread that's doing the exploit can go read that shared memory to figure out the highest resolution. That was how they got the highest resolution timer they could, right? So there's that, which is like, how do we actually engineer an exploit that gets us the metric that we need on a machine where a lot of things aren't available to us? That side, I can't help you with, right? That's the creativity of security research. That's what you folks are experts at. And I'm sure you will figure out many things like that as you go. The part that I can sort of shed some light on is, what do you do when you do have complete access to a machine because it's your machine and it's the machine you're trying to target? You've got one. So you can be in kernel mode if you want. You could do whatever you want on this machine because you've got root on it. And what you're trying to do is study its behavior so you can figure out where the exploits are before you try to craft that attack that's by definition not going to have access to a bunch of the things you could be doing on the kernel side. So does that make sense what I'm saying? Does that seem like a reasonable split?
Yep, spot on.
Okay. So let me talk about that because it's the part that I can actually speak to. The exploit crafting, I got nothing. So when you are on a machine that you control, you typically have access to a lot of information, and that information is a lot more granular than you expect. If you've never done this kind of thing before, or you're new to microarchitecture analysis, you will be absolutely shocked at the amount of different data, like probes, if you will, that they give you on modern hardware. So we'll start with the really basic one because you brought it up originally, so I want to explain it because you had asked about it. But then I'm going to show you like, well, there's all this other stuff, and you probably care about the other stuff way more. So very briefly, you mentioned read timestamp counter when you originally messaged me about doing this stream. And obviously, read timestamp counter is a pretty important thing. It's the x64 instruction that you would use if you want to get what is basically a chip-wide clock. So what happened was early on in the life cycle of x86, they introduced, was it Pentium era? I'm not sure. I don't think it was on a 486, but maybe it was. It was definitely on a Pentium, I think. I don't know. My memory, I'm old. My memory is fading. So I don't know exactly where, but point is a long time ago, right? Think late 90s maybe or something like that. They introduced this instruction called RDTSC, which would tell you the value of a like sort of actual, a number being kept by the processor, and it would go up every clock cycle. So literally you'd call RDTSC and you got back what clock cycle you were like reading it on, more or less. Like not exactly, but pretty darn close to that. That's what it did. And it's called read timestamp counter because it's just this timestamp that's like clicking up, right? So you read it once, you get one value, you wait some number of cycles, you read it again, and you get a value that's roughly how many cycles actually elapsed in between those two things. Now, what happened is as that sort of, Pentium line progresses and we get further into, it's mid 2000s now or something like that, we transitioned from that era of RDTSC to what's called the invariant TSC or invariant timestamp counter era, which is what we live in now. And what happened was as they started adding more cores, so remember like Pentium or something like that, there's one core. If you want multiprocessing, you have two chips in two sockets running two different Pentiums, right? You don't have one chip that has multiple cores on it. When they started adding multiple cores, right? Core 2 Duo and that sort of stuff. When they started having multiple cores, they decided we're going to make the timestamp counter be roughly matching across these cores. So when you do an RDTSC, you're going to get the same value back, regardless of whether you were doing it on this core over here or that core over there, right? Previously, that wasn't what was happening. You just get, each core is doing its own thing. And so each of their TSCs were just going up totally separately. They weren't synchronized at all. Now they were going to be synchronized. And that's the era that we live in now. So when you call RDTSC now, and the reason I bring up that history, just so you can kind of understand why it is, it's a little weird now when I describe what's happening. You're like, huh? It's historically, it transitioned. Now when you call RDTSC, what you're actually getting is sort of a broadcast clock value that all of the cores are observing that actually has, I mean, it might be a bit of a strong statement, but I'm just going to say it, basically nothing to do with how many cycles that particular core has gone through. Each core on a modern processor, I mean, you know how they love to talk about performance per watt now and how low power are you, how much power are you using in the data center, power, right? Each of the cores is now oftentimes clocking itself all over the place based on heat management or boosting up to try and get a little bit better on this benchmark or that benchmark, right? All of these cores are now operating at totally different frequencies. One core may be like basically completely asleep, and another core that's running some crazy tight loop is like boosting up to, 5 gigahertz or something. That's the reality of what a modern processor is doing. And so when you call RDTSC, what you're going to get back is this broadcast observed clock value that has nothing to do with how many cycles the particular core you executed it on actually went through. So that means if you take that with all the stuff we said at the beginning of the stream, that means that not only are you in this world where all of these micro-ops are happening out of order and we have really no idea where the instruction stream, the processor actually is at any given time, and all this other stuff, that is all happening on some clock that's totally separate from RDTSC. It's not counting instructions because the instructions are happening in parallel, right? That whole instructions per clock thing, cycles and instructions are completely decoupled by that thing that I talked about where this whole front end, back end executing multiple things at a time. So not only are instructions completely decoupled from core cycles, but core cycles are completely decoupled from RDTSC. So really, read timestamp counter is now just a wall clock. When you call it, you get back wall clock time. It's how long did it take between now and now based on some timing that is happening core-wide. Does that make basic sense?
Yep.
Okay. So that's what RDTSC is. It's great. We use it all the time in performance because it gives us a really high precision way to measure how fast something's going. And it's measuring how fast something's going in reality. It is a wall clock time, right? So if we want to know if something got faster, RDTSC pretty much tells us that. If you took less, if less RDTSC elapsed, right? If less of the timestamp counter elapsed between here and here, the thing got faster. Okay. So that's all RDTSC is. It's great, but that's pretty much all it does. Now, when you are analyzing a microarchitecture, because of that whole diagram I showed you before, oftentimes we want to try and know more than that. We're looking at this particular core, we're pushing a bunch of stuff through it, and we want to analyze what its behavior. So RDTSC does tell us if the thing we tested got faster or slower, but doesn't really tell us something like how many instructions per clock it executed, because we know between 2 points in our program how many instructions roughly it would have executed, right? But we don't really know how many cycles it took because we have no way of observing what its clock rate actually was. And RDTSC doesn't tell us that because that's just a chip-wide clock that's being observed by the core. It's not actually related to its cycle count. So, a couple different things we can do here. The oldest and most widely supported way, especially if you're on a machine that you control, this becomes much harder if you're not, is there's this whole set of things called PMCs or performance monitoring counters on Intel chips that you can enable. And the way that this works, and you'll forgive me for not going into too much detail because unlike you folks who probably spend some time in the actual kernel, I don't get to really do any of these things. We are not allowed to call these things in sort of user land. And so when we quote unquote use these, I typically have to use a program that has a signed kernel driver or something to do it. So I have to run like vtune or event tracing for Windows or something like that to get access to these things. On Linux, you use a utility like called perf, which you probably are familiar with, to get access to these things. But for folks who are security researchers, you can just do whatever you're doing, go into kernel mode. I don't know what you folks do, but if you're in a completely unlocked machine, you can just get them directly in. And let me explain how that works. So basically, there's this thing called write model specific register. And I'm sure you folks are familiar with this if you do security research. And what happens is there are model specific registers that you can poke at that hold settings. The settings for this that we care about here, there are some number, depending on the chip, there are some number of performance counters you can enable. You can think of it as the chip only has the capacity to track a few performance values, and there are many, think hundreds of different performance metrics that can collect. And so what you're going to do when you start this process is you or some tool you use is going to poke at the chip's settings and set a few performance counters that it can collect to the ones that you want to collect at that time, right? And I believe that happens through write MSR, but again, we're kind of outside of what I get to do day to day here, so take it with a grain of salt. But pulp reading, you set those things. Then once you have them set, you can do a thing called RDPMC. And RDPMC is basically the same kind of instruction as read timestamp counter. It's a thing that asks for the value of some counter on the chip. But instead of reading that clock that's observed by the core, it actually reads one of those counters that you enabled when you set up which counters you wanted. And so RDPMC actually gives you access to a ton more information. Way, 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 way more counters. Now I'm going to talk about two things here. First, I'm going to talk about cycles really briefly, because obviously that's very important. And then I'll talk about all the other things you can do. Now, the reason I want to talk about cycles specifically is one of the things that you can measure in the core with these counters, one of the things you can enable is actual cycles. So you can find out the old school TSC, right? The thing it used to be back at Pioneer, where it was just a count of how many cycles went by. You can get that. And that is incredibly important for observing microarchitecture details, because that's exactly what we want to know when we're creating little weird micro benchmarks to see, oh, how exactly many cycles did we go through when we did this thing, right? So RDPMC can get you that. Reason I want to talk about cycles separately is also, let's see if I have this here. If you happen to be on a recent Zen CPU, which a lot of people are, I love them. They're great cores. I have a Zen 4 core I absolutely love to death. There is a separate instruction called RDPRU. Now, I know this is a weird thing to say. It's like, wait, you're telling me that it matters exactly which chip you have? Yes. Even though x64 is supposedly like a uniform ISA, everybody has their little extensions to it. So like some chips have different instructions than others. That's just how it goes. AMD chips have this RDPRU. And what it does is it allows you, in the same way that you read RDTSC, to read an actual measure of cycles. And you can see here, we won't go into what these are, but there's mperf and aperf. You can read two different things. And those actually give you a way in user land, without having to set up the model specific register stuff or any of that. It actually gives you a way to read an actual measure of cycles. And this is really a good instruction for yourself if you do have a Zen 4 core, because it means that you don't have to be doing these kind of kernel mode things to actually count cycles. Just throwing that out there. Okay, so now let's talk about what you can do with these performance monitoring counters. If we go over to here we go. This is a little utility that I wrote. I don't recommend anyone use it. I just posted it on GitHub because it's something that people can quickly look at if they're unfamiliar with it. Basically, like I said, there's this utility on Linux, which I imagine a lot of you probably use. Not necessarily the utility, but Linux anyway, but maybe use the utility as well, called perf. And perf, like I said, allows you to access these things with the help of the kernel, right? You don't have to do your own, write the model specific registers and collect the data. Perf can do that for you. And so if you run a program using perf the way you normally would, a lot of you are going to be probably familiar with this, you can ask it to collect a number of different timing things for you. So this is great for people like me, right? Who, again, I don't spend my day working on kernel stuff, so I don't have a machine set up with like a signed driver that I can use to go change the model specific register and all that stuff. So I have to go through utilities like this. And this is a pretty good one for this type of thing. So what I did is I just wrote a little program that will do a batch execute of perf, right? And what it will do is just go through, this was on Skylake cores that I did this really, it'll just go through every performance counter I could find that is available on Skylake through perf and collect them all. And the reason I'm using this as a reference is the easiest thing to pull up. These are all of the performance monitoring counters you could ask it to give you. And I'm just scrolling through, right? It's nuts. You can see, remember I talked about those microops? Well, here's microops dispatched on port 0, microops dispatched on port 1, port 2, port 3, port 5. What is that counting, for example? I'm just picking one randomly here. Well, if we go over to, let's see if I can pull up a wiki chip of this. That was for Skylake, right? Here's an architecture diagram of Skylake. Remember I talked about front end. This is that equivalent to that on the Skylake architecture. Think Intel Core i7 7700, something like that. That series, I think is Skylake, right? It's that core generation. Yep. Well, I'll correspond to the diagram for you. Remember I said all these execution units, these are all the things the processor can do. It can do, address generation, and it can do, this is a SIMD add over here. This is a general purpose arithmetic logic unit over here, right? Well, here's an architectural diagram from Wikichip on Skylake. Here's that same equivalent of execution units. They're called ports on Skylake: port 0, port 1, port 5, port 6, port 2, port 3, port 4, port 7. All listed here. And here are the things that they can do. So when you think about microops, right, coming in here, renaming to use the register file, right, going into the scheduler, and then feeding these ports Anytime it's like, oh, I've got an add I can do here. I've got to do this memory move. I can feed this here, feeding, right? Throwing these things into these execution units. Well, there are 0 through 7 of those, right? And we go back to this. Lo and behold, here's all 7. What does this count? In between, the two RDPMCs, we do an RDPMC of this like at the beginning of our run. We do an RDPMC of this at the end of the run. The delta between those two is exactly how many micro-ops actually got fed to port 0, right? It's literally like a little toll booth counter right here. So you can count exactly how many micro-ops flowed down this port into this execution unit by using those performance running cards. And of course, it's got them all, so we could count exactly where they went. So when you think about what this gives you, right? And it here's branches, there's branches, there's cache, hits and misses. Let me see where we've got some of that stuff here, right? The front end, you can measure front end retirement. There's so many things in here that if you ask me to explain any given one of them, I probably couldn't, right? It's like you pick one of these and I have to guess, right? And so they have a little description here, right? Request from the L1, L2, L3 hardware prefetchers or load software prefetchers that hit the L2 cache. That's about all I would know about it, right? That's how many of these things there are. There's way more than I ever learned. And so if you're coming at this and you're like, I want to exploit this chip, I want to learn all of the ways that it does things. I want to see if some tweaky stuff I do in code is actually able to mistrain the branch predictor or force some kind of stall in this part of the pipeline or evict things from the cache in this way at this time. This gives you everything you ever wanted to know, right? And so what I would expect if you want to do this kind of exploit development is you're going to want to go take what CPU am I targeting? You're going to learn what are all the things it can provide me for performance measurement. And then you're going to want to start studying all the different code paths. How do those metrics change, right? And so that's kind of where I wanted to direct people. When you asked about timestamp counter, I'm like, the timestamp counter is fine, but this stuff is probably a gold mine for exploit development. That'd be my guess. I don't do it for a living, so take it with a grain of salt, but that's what I would say. So, a lot of options there. RDPMC, really your friend, way better than RDTSC because that can only tell you global observed clock. RDPMC tells you so much more. So there you go. So does that answer the question? Hopefully.
Yeah, it's interesting. A lot of information. It's going to send myself and I'm sure many people watching down a bunch of rabbit holes. Let me put us back up there together. Yeah, quite a few questions kind of came by here and there. So let's see. So Janik asked a question. I know someone answered a bit of it, but what do you think about this? Is there any way to dump a microcode from a processor to analyze it?
Way outside of my area of expertise. Sorry. Obviously, for performance, we just don't do any of that. My gut instinct would be to say no, there probably isn't without some kind of extraordinarily sophisticated hardware or attack kind of thing, just because I'm guessing that hardware vendors really don't want you to see inside there. But that is purely my guess based on how secretive they are. I have no idea because, again, for performance stuff, we don't do that. Obviously, for very old chips, people often reverse engineer the microcode by using a die shot, which is amazing because they can see how it's traced in there. Obviously, that wouldn't work on modern chips where the microcode is updatable. But so I don't know on modern processors if people have succeeded in cracking a microcode out of a processor. That would be fascinating if they could. I would love to see that. But again, really outside of my area, so I apologize. I have a better question for you. Again, I only look at performance, so that's where my knowledge ends. Sorry.
Yeah. There's been a lot of really interesting examples of that with people trying to recover crypto wallets and things, and being able to dump stuff off where they're not supposed to be able to dump. It's pretty wild.
Yeah. Okay. Yeah.
There's a question for you. You can see it, right?
Oh, yes, I can. Casey actually prefers neither. Casey is one of those people who, for some reason, really, 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 really likes to have their performance metrics on screen at all times while your program is running. So Casey reluctantly uses VTune when he has to, but tries very hard not to have to do so, right? So a lot of times I'm living by RDPRU or RDTSC, and I just kind of go by my intuition as to like, okay, I know roughly what's going on, so we'll do this. When I'm like, that's really weird, and I have to do something with a performance monitoring counter, I'm just sad, and I usually run VTune. Now, in my dream world, there's like some really cool driver that someone writes that lets me do WRMSR myself and collect the PMCs. And there sort of was originally a thing called WinRing 0, but it kind of stopped working / being supported. And so yeah, if there's some security researcher out there who wants to write the like thing that's a very, very easy, small thing that can do this, of course, maybe none of us would install it because it comes from a security researcher, so we think it's going to own our machines. But either way, I usually make do without those things, and so my preference would always be to be able to get these things directly, and I'm usually just sad and have to use the utility sometimes, but that's why I don't use them very often. Perf, the Linux utility, if I'm on I use that. It's actually, I like that utility, that perf utility. And that's why that little thing I posted used that, because it's just the easiest one for me to use. I find it more ergonometric than something like VTune, which always kind of, I don't click with it. Its interface is weird, and yeah, I don't know. So sorry, I don't have a better answer, but yeah, I just wish I could. I wish I could put my Windows in a mode where I'm just like, look, let me call WRMSR. Just let me call it, dude. Like, but you know. There's Xperf and stuff like that on Windows as well, but you know, I don't like them as much.
Do you have any good recommendations for learning more about this stuff? I know you published a lot of things, and any books or resources?
Not really. That's why I did Computer Enhance. That's why I post all the stuff that I do, is because I didn't think there was stuff that was in the way that I feel like it's, you know, because one of the problems is it's pretty easy to go find something that just kind of talks about this stuff, where you're like, oh, here's some person talking about specifically RDPMC or something, but you have no context for like what that is. And if you haven't like worked through a bunch of examples yourself, you just don't really, it kind of bounces off, right? And so what I try to do is like make basically things where here's like little bite-sized pieces. Okay, like let's try to time this little thing. Okay, let's learn about how memory moves. Let's learn about this. Let's learn about that, slowly and gradually, so you can kind of build up your intuition until it's all just very second nature. And then you have access to a whole world of information where you can just kind of pick and choose, like, oh, I can just go read something some expert wrote on RDPMC now, and I know what they're talking about, and I can employ it easily, right? So, you know.
Yeah. Akimbo has a funny question. It's, hey, any insights on how the people at Quake come up with the fast inverse square roots? and also, what are cache misses?
Okay, so those are two totally separate questions. I'll start with the first one. I don't totally recollect what the Quake inverse fast square root is. So let me just preface by saying take it with a grain of salt. But my expectation for how a fast square root would have been done at that time is, first of all, so the reason they're going to be doing a fast square root, let's start with that, because this is important to understand. The reason they're going to be doing a fast square root is because they want to renormalize something, right? Typically in game engines, what you have is you're doing some work and you need to modify some vector that was supposed to be normal to begin with, meaning it's supposed to have a length of 1, right? Some vector is pointing some direction. In Quake's case, it's 3D. It's going to have a length of 1. So it's 3 components, x, y, z, and x squared plus y squared plus z squared square rooted is supposed to equal 1. That's just like the normal criteria for a normal vector. And so what's going to happen is you're modifying that vector, and then you need to make it so that it gets renormalized. It's going to like shrink a bit or grow a bit, but you kind of know it's not going to be too much. That's usually where a fast inverse square root comes in. We know that we can start with the assumption that the vector is near, its length is near 1. So we don't have to handle the case where the length is 10,432. We're just pre-saying like that's not going to happen, right? And so the way that you would typically do a fast inverse square root in those days is first you would go, let's use the tangent line approximation. Let's assume that we're somewhere close to 1 and we just need to get back to 1. So if you don't know what the tangent line approximation is, go look that up. It will tell you you're basically just using like a first derivative to try to shoot towards where you're going. And so what they probably did is wrote the tangent line approximation for inverse square root. And then if I vaguely remember having seen that inverse square root code that you're talking about because it kind of gets posted around the internet from time to time for whatever reason. People really love it. Because floating point operations were slow at that time, they would have done IEEE tricks. What they're going to do is like, oh, instead of doing a reciprocal or doing some kind of divide or doing some kind of multiply or whatever I was doing there for the tangent line approximation that I needed to compute, I'm going to go manipulate like exponent or mantissa bits a bit to do weird stuff like divide by 2 faster than it is to multiply by 0.5 in floating point. And so you're going to see some ridiculous crap like casting the floating point number to an int, screwing with the bits, and then casting it back to a floating point value. That's all they're doing, is directly mucking with the exponent and like significant and that kind of stuff. You would never, ever, ever want to do it that way these days because you're going to have to, it's going to have to be kept on the SIMD side of the chip. So you're not going to downshift that way. You might do bit twiddling, but you would be doing it in some way that was like one of the, you know, SIMD PS side of things. So it's going to be like a wide multi-element one. And you're only going to be doing that if you're doing some kind of acceleration for a really crazy transcendental, like, you know, LDEXP or POW or something. If you're just doing things like reciprocal square root, multiplies, divides, that stuff, the chip is super fast at those now. So you would never see something like the Quake error square root where you actually drop down to the bit level fiddling. Instead, what you're going to see is it just calling the reciprocal square root instruction, right? Because it's there and ultra fast, right? So I don't know if that answers that question. That's about, you know, again, not security focused. So let's just leave it at that. What is a cache miss? Is that the other question?
Yeah.
So a cache miss is pretty simple. When you are talking about ancient chips, they used to read memory fairly directly. So when I talk about loading some data or an instruction into the chip, I'm talking about literally going out to the physical RAM sticks that are sticking into your motherboard, and I'm asking that bus to transfer a bunch of bits back to me, and that's what we used to mean by reading memory, right? That is too slow, so modern processors now employ a series of caches. There's an L1 cache, which I mentioned at the beginning of the stream, an L2 cache, which we saw in the diagram, typically an L3 cache as well, but not always. Depends on which chip. Like I said, M series, I think, are just L2. That's the last level cache. Sometimes an L4, but rarely. Some modern Intel chips are reintroducing that. And then main memory. And what you can think about these are successively larger and slower little memory subsystems that sit between the core that's doing the execution and the main memory. And they store recently used locations in memory so that you don't have to go all the way to memory to get them. So when the CPU now tries to do something like load a piece of data or load the next instructions it's going to do, it goes and asks the different levels of cache in order, essentially, they're getting asked to provide that. It first asks the L1, do you have this piece of memory I need? Yes, no. Then it asks the L2, do you have this piece of memory? And it's not really it asking it. It's like the L1 will then ask the L2 will ask the L3, the L3 asks the L4 is maybe a better way to think of it. Although all this is pretty fluid and just kind of more of a theoretical model that you can think of. It's not exactly what happens on the chip. What we call a cache miss is at any one of those levels, if you asked for something and the cache didn't have it. That's what we call a cache miss. So it goes, I need this particular piece of data. It asks the L1 first. The L1 says, I don't have that. I've never seen that piece of data. I don't know what you're talking about. That's a cache miss. That means it has to go out to the next slower, larger cache, the L2, to see if it's there. Mm-hmm. Now, a cache hit is the opposite. We say we hit the cache if we ask the L1 and it does have it. So cache hit, cache miss, that's the nomenclature for it had it or it didn't have it. Now there's one other thing you don't see mentioned very often, but if you're talking about microarchitecture, which is sort of the theme of this presentation, there's one other thing that's not mentioned as often, but that's actually sort of like another level of hit or miss. When you are actually going to ask for a piece of data, it's not just the L1 that might have it. Because these processors are sort of doing things in this giant pipeline and things are out of order and things take a while to retire and all this other stuff, when you first go to ask for a piece of data, it also, in addition to checking the L1 cache for it, it needs to do an additional check where it checks the store buffers. Store buffers are the things where you write to memory, things go into these store buffers, and that's how they get stored out to the L1 cache or further. If some data is in the store buffer that it's going to, put back to like an L1 cache or an L2 cache or who knows what it's doing. Like I said, I don't know at the hardware level. We don't get a lot of these details, but however it's architected, it's going to go put it back to the L1 cache. Obviously, the chip doesn't want to read stale data. So if there's a store in flight that hasn't yet been committed back to the cache that it's talking to, it needs to first make sure it looks at the buffers on its way to those caches to make sure that if that data is actually in flight on its way out, it gets it from the store buffer. We call this a load hit store, meaning that instead of hitting a cache, you hit a thing that was on its way to a cache, right? And so if you're trying to understand microarchitecture, you need to understand both the concept that caches can have pieces of memory, but also buffers on their way to caches can have pieces of memory, and those can hit as well. Does that make sense?
Yeah.
Okay.
That's good stuff. Yeah, I don't want to keep it too long, but let's go. You have time for a couple more questions?
Sure.
Otherwise, people will keep you here all day because it's not often you get a chance to ask someone the hardware expert questions. So,
I mean, the other thing I'd say is I'm not a hardware expert, right? I do the best to answer these questions because I've found that very few true hardware experts talk to anybody, right? So I don't think of myself as a hardware expert. I think of myself more as just somebody who's okay talking to people who has tried to learn as much of this stuff as I can. But hardware experts know a lot more than I do. Believe me. Some of them are out there probably cringing right now going like, Casey, you forgot to mention the blah or whatever, right? So I always try to caveat the things I say with like, look, I do the best I can. I focus on performance and I know things about how to make CPUs run quickly, but the real hardware experts know way more than I know, right? So I do the best I can, but.
No, it's good stuff. Can you hear me okay? Because my camera's acting weird.
Yeah, you're just fine.
Okay, you can't see me though, right?
No, I see the OBS sort of virtual camera not enabled on the screen.
I'll keep messing with that, but as long as you can hear me, it's what matters here.
Yep, I can hear just fine.
Yeah, let's grab a couple more. Here's one from Philippe. Says, what do you think about Intel's ISPC compiler? Any thoughts?
Yeah, so I don't really use it, and that's because it's limited in terms of when you can use it, right? You have to be using a specific back end to have access to it, and so I always kind of feel like I don't want to lock myself into something like that. But I love the idea, right? I've always kind of liked the idea of like Chapel or, like shading languages, right? I love the idea of things that allow you to write code that looks more like scalar code, but that's easy to then turn into nice parallel, SIMD streams. And so I love the idea of ISPC. Do I use it myself? No. Would I like to see that become more standard? Yes. And that's really all my thoughts on ISPC. I still, maybe because I'm just old-fashioned, I still hand roll my SIMD stuff for the most part using intrinsics. And, I'm not saying that's great. So yeah, thumbs up to things like ISPC that are trying to make a difference there. Have I switched myself to using it? I haven't. But that's not because I think it's bad. It's because I always get a little worried about non-standard things like that, where I don't know if, oh, and I can't use that if I have to go port my thing to PlayStation 5 or something. I don't always feel comfortable using things that only exist in like one backend, or that only exist if you use a certain tool stream. And that's just me being a little bit old school and having had to ship for wide arrays of platforms and support multiple compilers in the past.
Okay, great. Here's one from Jack that I missed from earlier. Do you have anything special to minimize performance interference from other processes? Kernel context switch.
I don't, and I find that is very unlikely to be necessary these days for the things that I do. Now, for the kinds of things that security researchers are contemplating, that may be more of an issue. I can see why you might want to do those sorts of things. The reason I don't find myself having to do those things anymore is because nowadays we're kind of spoiled. Like my main dev machine, I paid like $500 for the processor. It's a 7950X, and it has 16 cores, right? So it's pretty easy for me to just run things. If I want to test something, I can run it on 8 cores, and I don't install, I don't allow Adobe Creative Cloud to be installed on any of my dev machines, so I don't have to worry about anyone sneaking in there. So mostly if you run on some smaller subset of your cores, some of the stupid Windows service crap is going to be interrupting some of your other cores, but that's okay. I don't need to test on all 16 cores typically, especially because when you're talking about performance, a lot of times you have to be able to target down a little bit. If your algorithm only really works when it's got all 16 cores and all 32 hyperthreads all to itself, well, most of your consumers at this point don't even have 16 cores, so not very smart. So typically I find that I don't need to do that for actual performance tuning for the sorts of things I do. I apologize for not having a better answer to that for security though, because I could see that mattering to you. What I can tell you, people like Agner-Fog. One of the things I didn't mention, for example, is the Agner-Fog optimization instruction manual. I should mention that now because this is really, really great stuff that I highly recommend anyone out there who's doing security research and gets into this stuff. If you're the kind of person who looked at these PMCs and was like, ooh, I'm going to go try that stuff. Agner-Fog, you can actually literally type in AGNER space FOG. Agner-Fog, he has these manuals. This is one of them. It's, let me see if I can get back to the beginning there. Microarchitecture of Intel, AMD, and VIA CPUs. And this is a manual that Agner-Fog and sort of a community of optimizers that he talks to and works with. There's forums and stuff. When a new processors come out, they actually have code. I think their framework. Their framework is actually public as well that they use for this. They boot the processor directly into their own control right out of the BIOS. And then they manipulate all the cores themselves to get rid of any operating system at all. It's just the BIOS and them now. And that's what they use to try to determine microarchitectural details. And if you're doing security research and you go ultra hardcore, right? And your knowledge at this point will far surpass mine. So you're going deep. This is the manual for you, right? I read it all the time to learn these things that they have discovered that I don't boot out of the BIOS into my own code to run things at this level, but they do. And if you go look, for example, I showed you that Intel Skylake pipeline. You want to know something really complicated about it, right? You want to know, okay, we were talking about those load hit store things and like that, right? You can go in here and read something, and they will say, okay, the Skylake processor can forward a memory write to a subsequent read from the same address under certain conditions. Store forwarding is a 1 clock cycle faster than on previous processor, right? They figured all this stuff out. They don't work for Intel. They didn't see a design chip. They actually time all of these things, like load hit store penalties, like all that sort of stuff. They time them all, and they write it up in meticulous detail for you, right? And everything that they can figure out is documented here. So if you are the kind of person who's like, I'm going to go hardcore on this, I'm going to set up a test machine. I'm going to boot directly out of the BIOS into my own code and get rid of the kernel for the OS and all that other stuff that might be running so that I can get pure, unadulterated results. Yes, you can. These are the kinds of people who do that. Their framework is public. I think you could just go get it. If you search for Agner Fog, he's got a whole web page. I think they've put it on there for you to use. And what's more, there's a whole community there that you can interact with, talk to, ask about these things. And if you become super baller at this, like I said, your knowledge will supersede mine at that point easily. You could also contribute back. You could be someone who helps document the Zen 5 on here, which will be coming out soon, right? Or whatever Intel's new chip is, and so on and so forth. So I would highly recommend taking a look at that community and these resources. If you're the kind of person who's sitting there going, how do I get the operating system out of my way? Well, you're in this zone now and way past the kinds of things that I would normally be looking at.
Awesome. Yeah, so I don't know what's up with my camera, unfortunately. It kicked me out.
All right, sorry.
Oh,
maybe that's also because you didn't subscribe to Twitter Premium. Maybe you don't even get a local camera now.
Yeah, something's going on. I have to figure that out. I already gave Elon all my money. But cool. Yeah, let's wrap it up there. That was awesome. I mean, super great stuff. I saw a lot of comments. People are like, whoa, this is really amazing stuff. Got to go do some studying now. So absolutely always the way things are with learning new technology and the way things work, especially at this low level.
Awesome. Well, I'm very happy I could add something. Like I said, security research, not my field. So I hope that I was able to provide sort of a gateway into the kinds of stuff that we do for those of you who don't already know it. And that will prove useful when you're looking at security stuff.
Yeah, and we put the banners up again. Follow Casey if you haven't already, and check out his site at computerenhance.com. And do you still do training? Do you do live training or in-person training?
We don't do live, but basically, it's basically a sign-up thing. It's like $9 a month on that site, and I just post content every week that goes over exactly this stuff, right? So we go through, here's how CPUs work, here's how to create some little benchmarks to see how they go. Again, focus on performance, not on security, but that's just what we do there. So if you want to learn how to do things like read these CPU diagrams, what's the front end doing, what's the back end doing, we basically we focus on giving people intuition by constructing little test cases where you can kind of see, oh, if I change this, I can see this effect happening, and that we said is happening in the front end. I can actually see it, right? Because I find that that's really the way that people build up their interest. They can actually see these things happen. So we focus on learning to read assembly language, learning how to make these little tests to see how things are happening. And then we also try to apply that back to a performance context, which again, that part will be a little less useful to security researchers, but all of sort of the micro benchmark stuff we do in that is probably right up their alley, and the sorts of things I was talking about today, obviously.
Awesome. Yeah, great deal too. And also, I think like me, many of us are now questioning what we're seeing in the debuggers these days, starting going forward. So things are
it's all true, right? It's like that's what the CPU is trying to produce for you, right? It's just that's not how it does it anymore.
It's dumbing things down for us, debuggers. So.
Yeah.
But awesome. Well, have a great weekend, and everybody else have a great weekend. And thanks again to the members on here. I appreciate you. And I'm not sure what's going on next week. I'll figure it out. DEF CON's obviously coming up in 2 weeks, less than 2 weeks. But anybody going there, definitely let us know. And jump on the Discord if you haven't jumped on it already. And hopefully we'll have you back again, Casey, if you're interested in joining us again. It's awesome.
Absolutely. Anytime. Thank you so much for having me on the program. It's been a pleasure.
All right. Bye-bye. Thanks, everyone.